Okay, in this part, let's take a look at image quality analysis, essentially a metric, noise uncertainty quantification that we have developed to analyze the effect of noise, how it changes the signal in your subject, and how you can use it in group level analysis. Before we get into image quality analysis, let's take a look at what is done or what are the common practices of analyzing noise, right? So let's say this was your noisy data. You get your denoised data from whichever is your favorite method. And this is your residuals. Residuals are nothing, but you subtract the denoised data, and from the noisy data, you take the absolute value or the root mean squared value, and you will get this residual map. And one can also get the standard deviation if you use a model like MPPCA, which essentially captures the standard deviation of noise, right? Both these measures, however, are very qualitative in nature, in the sense that you have to visually inspect and see that there is no structure in the residuals, meaning that no signal was suppressed, right? And it is also not very informative of how the removal of noise or the nature of the noise that was removed affects the downstream tasks, such as microstructure modeling or group level analyses. Just to show you a quick comparison, let's say we had this standard DTI protocol type acquisition. This is from the UCLA dataset. I believe this is a schizophrenic subject. And what you see over here is the non-local means denoising, MPPCA denoising, and patch to self, right? And if you look at it from a macroscopic perspective, all three perform more or less the same, right? We know that non-local means is supposed to do some smoothing, which is obvious in like this highlighted area, but MPPCA and patch to self do not really do not remove the signal from the data. So you can see that there is no spatial smoothing in patch to self. In MPPCA, there's some residual noise. In patch to self, the suppression is better. But what we really care about is not the visual quality of the image, but also how it affects the next steps that we will use in analysis. So before getting into the analysis, let's look at what image quality assessment means, right? So image quality assessment is supposed to achieve both of these objectives. One is that you want an objective metric that is either a quality map that goes beyond the residuals and the standard deviation map, and you also want a summary score for that map. This will become clear when I talk about the metric. And second, and most important, is that we want it to be in the absence of a ground truth reference image. Because in reality, when in any imaging mechanism, you don't have a ground truth unless it's simulated. So in traditional imaging, there have been different approaches to assessing the quality of an image, right? So the first one is the structural similarity quantification, which essentially is done by the structural similarity index metric, SSIM. There is the natural scene statistics, which basically sees how smooth or edgy the information in your images. You have visual attention models, which are based on psychology, or rather how the visual processing happens in the brain. And the last one is machine learning based models, where you develop a metric, or rather learn a metric from an image. And this is more common in super resolution, where you want to learn a perceptual metric from your data. So let's take a look at the structural similarity index metric, which I believe is the most famous one, right? So let's take a look at the image at the bottom. You have an image, let's say this was your ground truth, and you add Gaussian noise to your image. So this is uniform Gaussian noise with a fixed standard deviation that you add to your data. And when you denoise it, you will get your residuals that look somewhat like this, right? Or rather, if you knew you had the perfect denoiser, your residuals would look like this, where you don't see any structure in your residual map, right? But in reality, from a perceptual perspective, that is not true. Like, for example, if you see the banded patterns on her scarf, you can see that that part is more distorted, especially if you see the edges, or rather the folds in her scarf. And this is the whole idea of SSIM. And what it aims to do is separate the structural distortions from the non-structural distortions. So, for example, areas of her face or even in the background which are smooth are not that distorted when you visually look at it, as opposed to how the edges and folds in her scarf are. And same goes for the Albert Einstein picture on top, where visually the differences between the reference image and the test image are imperceptible, but there is an error map that goes on, and it captures even the slightest distortions in your data. So how SSIM works is it takes, let's say signal X is your noisy image, signal Y is your denoised image, right? It takes both of them as input, uses luminescence, contrast, and then combines them to get a similarity measure. However, in the case of diffusion MRI, this is not particularly useful because you want like visual perceptibility or visual conspicuity is of importance, but not that high importance. We care a lot about if we are losing essential signal information that we want to model and do tractography or do group analyses on. So that is why we built this metric, which is based on uncertainty quantification. It requires two key components, which I'll talk about first, and then explain how the metric works. So the first metric, the first component that you need to understand is the Bayesian uncertainty quantification. What Bayesian uncertainty quantification is nothing but taking any model, any microstructural model that you fit to your data. I believe in the morning today you have learned about DTI and DKI, right? Let's say you take these two models. You can reformulate these models from a Bayesian perspective. What that means is you will, instead of getting a fixed point estimate, like for example, in DTI, you get a fixed point estimate of your ADC or FA, right? Which is one value per voxel. Now you can get a distribution of all these values. And this was shown in the paper from Jens back in 2018, where essentially the key finding was that the fixed point estimate that you get from your DTI or DKI model is equivalent to the mean of the posterior that you can estimate from this Bayesian formulation, right? And you can also estimate the variance in the fit. And this is what we will leverage. This is the first key component that we will leverage in NUQ. But it is important to say that it does not have to be this Bayesian formulation. You can pretty much use any generative model. So for example, if you were using a neural network to fit to your data, you can easily get samples from the posterior and you can use that. The key point here is that you need only samples from the posterior. So the posterior does not always have to be in the closed form. The second key component that is used is the maximum mean discrepancy. So maximum mean discrepancy is a metric that I believe was developed in 2007, and later there was this very famous from Arthur Breton in GMLR in 2012. Right. So let's say you have two distributions. One is P and one is Q. Right. And these distributions look somewhat like this. And we get sample. Let's say we sample from this distribution. What the MMD metric does is compares the mean of the kernelized form of these samples. So what it does is, let's say you sampled from your you sampled X from your distribution P and sampled Y from your distribution Q. It will, sorry about that, it will pass it through a kernel and it will take the mean of that. So you can see that if you expand out the MMD equation, it is expectation of the kernel of X transpose and Y transpose, which are essentially the samples from the two distributions. And you subtract the since it is the square, right? You subtract the cross term. And what it is really doing is it is accounting for within sample similarity, and it is penalizing the between sample similarity. And so when we implemented the maximum mean discrepancy metric, we allow for linear, Gaussian, polynomial kernels, and whatnot. And I'll talk about that in the next slide. The very nice property about maximum mean discrepancy is that it manages to capture differences in distribution, which are very subtle. For example, here there is similarity. So the maximum mean, so the blue distribution and the red distribution, there is similarity. So the maximum mean discrepancy is higher in that area. But let's say the discrepancy between the blue and the red distribution here is very high along this area. So the MMD score is also very high, right? So we want, ideally if the distributions were the same, the MMD score would be 0. But even if there is a small difference between the distributions, MMD will capture it. And this is owing to the nonlinear kernels that you can use within the MMD. We can also use any other two-sample testing, such as the ones that come from optimal transport, like Wasserstein distance, or you can use the KS test, which I will talk about in the coming slides. So how does this really fit into how do we use these two components to create NUQ? Before getting into that, let's just look at the basic workflow of diffusion MRI and where NUQ is plugged in, right? So what you see over here is a typical diffusion MRI analysis pipeline. You have your data, you do some standard pre-processing, like here I'm focusing on denoising, but since it is like the first thing that you do on your partial data, and you do some eddy, motion, susceptibility, and whatnot your data requires. Then you do some biophysical modeling, which is basically an inversion, like a model fitting that you do to your data. You extract microstructural measures, and then you do your analysis. So NUQ is plugged in at these 2 points. So first, we measure the uncertainty of the metric that you are extracting from your microstructure model. So for example, if you were using the DTI model, like the standard diffusion tensor model, you can get a bunch of different metrics such as FA, right, or mean diffusivity, MD, out of your data. FA is fractional anisotropy. And you can quantify the uncertainty of like essentially the variance of how the FA is varying in your data. And you can summarize that using the maximum mean discrepancy, which in turn generates the NUQ score. So just to look at it in detail, so the row on top that you see over here is the raw data, and the one on bottom is the denoised data. So if you take the raw data, right, you will have some variance in your model fit, and that variance will decrease as you denoise the data. Like depending on the denoiser, this variance in fitting, or rather the standard deviation of the fit, will reduce. And we can capture that reduction by the difference in the posterior that you sample, that I just spoke about in the previous slide, that you sample from your microstructure metric. So for example, over here, from your data, let's say you computed FA, like you wanted to see like how the FA would be affected, right? You just sample two FA samples and you compute the maximum mean discrepancy between them, and you get a quality score out. So on top over here, I've shown the entire workflow where you can take a diffusion image, you do your model fitting, you do your uncertainty quantification. From your uncertainty quantification, you will get your quality map, the new quality map, and you can then pool that into a scalar score, which we call as the NUQ quality score, right? And you also get this additional NUQ quality map where it shows that the uncertainty in different boxes, like in different areas, how the uncertainty is. And you can see that like on raw data, the uncertainty is higher in like the central region, whereas in the denoised data, it's much lower. So let's take a look at how this NUQ score performs on different models, metrics, and on different subjects. So the one that you see on top over here is the return to origin probability metric that you get from the map model, which I believe you will learn on Tuesday from one of the presentations. This this RTOP measure, which comes from the map model, is on multi-shell data. So the one that you see over here is raw data denoised with MPPCA, non-local means, and pasture self, right? And we know that, like for example, non-local means is supposed to smooth the data, right? But you can see that the NUQ quality maps are not really affected by smoothing. So it does not mean that the smoother the quality map, the smoother the data, the better your quality map is going to look. Not really, right? And the one in the middle is from the schizophrenia cohort from the UCLA dataset. And this one, you can see that MPPCA does slightly worse, does slightly better than the non-local means, and the performance of MPPCA and pasture self is kind of similar when you look at the quality scores. But when you look at the RTOP measure from the multi-shell data, you can see that pasture self is much better as compared to MPPCA and non-local means. So the one measure that we're seeing over here is FA, the one here is RTOP, and the one on bottom is from a Hardy protocol, which is a very standard data set that we use in arXiv. You can see that with denoising, this NUQ score decreases, and here the non-local means is doing slightly better than MPPCA. So implicitly, you can use NUQ to choose a denoiser that is well suited for your data. We don't know a priori which denoiser will work better, right? And additionally, with NUQ, you can also get the variance of your model fit, or rather not just model fit, but the variance of the metric that you have extracted from your data. So for the DTI model, you can see that the raw data has a lot of variance, MPPCA reduces it, non-local means also reduces it, but you have some structure which is harder to see given the size of the image. Sorry about that. And the variance is much lower with pasture self. Another key feature, and this is what was one of the main objectives of NUQ, is that it allows not only for like a global quality score that you see over here, but it also allows for patch level quality scores, right? So for example, if you were interested in particular areas of the brain, like ROS, you can pick those out and you can compute a patch level score. So for computing a score for the entire subject, we propose using the linear kernel within the maximum mean discrepancy computation. But if you're going for a patch level, you want to account for that 2D or that local structure. And I propose that you use the polynomial kernel. And you can even go at a voxel level, which is essentially what this NUQ quality score is. And so now that we know that MPPCA is more or less doing better than non-local means, and pasture self is also like coming closer to MPPCA on this LA5C cohort. Let's see what it does on the 20, like I just randomly picked out 20 subjects of controls. And you see that like the variance of the NUQ scores kind of reduces with MPPCI and it is much lower with patch to self. So this brings me back to my original point that noise will have a different effect on each subject, right? And you want to essentially account for that. So it's like a quality score for each subject and it is agnostic to what denoiser you use. So next key focus of why we developed this is to analyze group level differences. So TBSS is one of the most standard analysis tools. It stands for track-based spatial statistics, where essentially you extract a skeleton of the white matter from your data and you analyze group differences based on that, right? So what I'm showing here is the group difference between healthy controls and schizophrenics before denoising and the one after denoising. And you can see that you see a lot more group difference in different areas of the brain after denoising. And we use NUQ to essentially quantify that. How we do that is we take the raw data, we denoise it with patch to self, we sample 100 FA samples, we do a Bayesian t-scoring, like a Bayesian analysis to quantify this group difference. You can do your favorite type of statistical analysis, even the one which is there in TBSS by default. And you will see that NUQ can actually quantify that, right? And to quantify this, essentially, we divide it by the variance that is extracted from, rather the standard deviation that we get from NUQ. We are also, okay, so basically you see that the areas where it is orangish yellow is significant, like is FA, where schizophrenics have lower, it is areas where schizophrenics have lower FA as compared to controls, and the blue areas are where schizophrenics have higher FA as compared to controls. So it is, so that's why we use like a divergent contrastive map. And there is a very strong correlation between areas where the denoised output has a higher difference among schizophrenics and controls. We also do this on randomly sampled voxels across all. So we used, I think, 40 subjects, 20 controls, and 20 schizophrenics. And you see that before denoising, the distributions are kind of, you know, for different subjects, the randomly sampled voxels have distributions that are kind of intermingled with one another. But after denoising and using NUQ, you can essentially see that this difference, like rather NUQ is helping quantify this difference between the controls and schizophrenics, which also explains the previous output, right? That the confidence, like since the variance or rather the uncertainty in the fit is reducing, you see that the PDF gets, rather the distribution becomes sharper, you have a higher confidence, and we show that with the group mean posteriors. So for example, the two small distributions that you see over here are schizophrenics and controls, but after denoising, like this difference gets very sharp. Well, this is just a preliminary analysis to show how you can use NUQ in quantifying or rather in computing group differences. It's not the most perfect analysis. Right. And while we propose using maximum mean discrepancy within NUQ, you can pretty much use any other two-sample testing approach. So for example, we compare against Kolmogorov-Smirnov test and the Wasserstein distance. You see that maximum mean discrepancy captures more variance as compared to Wasserstein and Kolmogorov-Smirnov test, but they also do compute the differences, and you can use whichever one we want. We will provide that in the implementation. The code will soon be integrated in Dipy, but you can always reach out to me and you can use the code. It is pretty much ready. I will try to provide it. And good luck with the rest of your workshop. Thank you for listening to me.